Today's lesson will be about matrices again. So we have 2 more lessons on matrices, and you really should pay attention to this one. It is the most important lesson on matrices and probably the hardest class of the hardest lecture of the whole matrices unit, and probably the whole course too. So this will be pretty confusing if you don't take notes, right? So hopefully you have your notebook ready and you're ready to take notes, because this is going to be quite confusing. Quite complex how you do it, right? So today we are going to learn about matrix determinants. Our schedule is we're going to go over the homework, go over determinants, go over Kramer's rule, and then some problems. So let's just start with the homework. And remember, you have to do this using Gauss-Jordan elimination, right? Using Gauss-Jordan elimination. So let's do this real quick. And hopefully remember the row operations that I taught you. Okay. All right, so I'm going to go over this now. So first, when you're dealing with one of these, you have to, you must make it into an augmented matrix. So as you can see here, we have our coefficients and our constants. So we can just make that into a matrix, just about this big. So it's going to be -2, right? -1, -1, -11. You can see all the coefficients are in the matrix. That's how we're going to manipulate the system. 3, 4, 1, 19, 3, 6, 5, and 43. As you can see here, this is the x column, the y column, and the z column, right? So now we have to use row operations to try to come up with something like this. As you can see, we must isolate each variable, so then we can get the actual values of variables. So this is called an identity matrix. We must have that. And to do that, we're going to need to use what we call a pivot. And I'll show you that how to do that later. So let's have a game plan on how we eliminate this. So first I see like a pivot in the Z column. A pivot is basically an element of 1 or -1, and we can manipulate that to get rid of the others. So let's just see what we get, right? So let's just see what we end up with. So let me do this. So we have this pivot here of -1. We can basically just add row 1 plus row 2 to row 2, and that just eliminates and simplifies some things. So of course row 1 is remains the same. Row 3 also remains the same. Row 2 is basically row 1 added to it, right? So we're gonna have 1, 3, 0, and 19. As you can see that the Z element of row 2 is eliminated now. We can actually continue to do this. Let's continue to do this for row 3. So we still have this -1 pivot here, so we can just do that as 5 times row 1 plus row 2, actually row 3 to row 3, and our result, row 1 of course is unchanged. Row 2 is also unchanged. Row 3 is now gonna have 1, 5, and actually no, wrong. It's 5 times row 1. So let me redo that. So 5 times -2 plus 3, just -7 here. And then we also have 5 times -1 plus 6 is 1 here. And then we have just 0 here. And then 5 times -11 plus 43 is going to be -12. So as you can see, we have completely eliminated the Z elements except for 1. And now that we have an isolated Z element, we want to have an isolated X or an isolated Y. So let's just see which pivot we want to use here. And I think we should use, in the second column, we should use this pivot and then use this pivot for Z. So then we have 3 of these, right? Let's continue on with solving this. So we have, let's just do row 3 plus row 1 to row 1. So row 2 is unchanged, and row 3 is unchanged. But row 1 is going to basically just be added here like this. So as you can see, we eliminated another element, and then let's just do the same for row 2. We have row 3. Actually, let's do this. How about -3 times row 3 plus row 2 to row 2? Row 2, yeah. Yeah, so we have something like this. So row 1 is just the same. Row 3 is the same. Row 2 is going to be, so it's going to be -3 times -7, it is 21 plus 1. And this is just going to be 0, and this is just going to be 0 as well. Okay? And so this, we have what? We have, well, that's bad. So we have 36 plus 19, which is 55. But then we have some weird coefficients here. It's not really ideal. So I don't know what to do with this. We could definitely add them using like common common multiples. I don't really want to do that. I think we went the wrong way here. I don't think let's try this again. So if we use the pivot in column 2, we end up with something like this, which is not exactly ideal. Right? So let's start over. Except we're going to use column 1 this time. The pivot on column 1, which is this one, right? So honestly, we just need to yeah, I probably should have started with column 1 because you can see the numbers are big, and hopefully we eliminate those. So we're gonna take 2 times row 2 plus row 1 to row 1. As you can see, we have 0 here. We eliminated that, so let's just write what we have. Right? And then we have 2 times 3 times plus -1, which is 5. And then we have just -1 here left. So 2 times 19 plus -11 is 38 minus 11, which is 27. Okay? Make sure to correct me if I'm wrong about any of these calculations, but there could be some difficult things here, calculation-wise. So now we have that. And finally, let's see, we have to get rid of the stuff in row 3, right? So we can use the pivot again. So let's just say negative. Actually, we don't need negative. We just need 7 row 2 plus row 3 to row 3, right? Okay, so first two rows unchanged, 1, 3, 0, 19 unchanged, and then we have 7. All right. So this is it's gonna be 0 here. We're gonna have 22 here, which, oh my gosh, we're gonna have some ugly numbers again, unfortunately. Yeah, but we can't really do anything about that. So 7 times 19 is extremely ugly. It's like 123, right? Hopefully it is. Anyways, no, it's not 130. It's 133, right? So 7 times 19, 133. Minus 12 is 121. Okay. So I'm probably not going to do this right now because it just takes too much time. But if you do want to continue to solve this problem, as you can see, we have isolated these two pivots. Now we just need to work on the second column here. So probably using 3 as just like basically like a common multiple thing, right? Kind of like elimination within the matrix, right? Hopefully the next one has some better numbers. I don't know why this problem has 3x plus 6y plus 5z is equal to 43. It's just, why is there a 43 there? 43 is another ugly number that I don't want to work with. Let's check if this one is better. So this one, let's just see how we do this. Hopefully we don't run into any more ugly numbers, but the one that I just did is perfectly solvable if you just spend some time looking at the common multiples. Then you can. All right. So are there any questions though so far about this? If not, then I'll just start with this one. Continue to do this. So let's see which column. So obviously columns 1 and 3 have pivots, these ones here. I'm thinking that we start with the first column. I don't know if we're gonna turn out to have any good numbers or bad numbers, but let's try. All right. So let's just do 2 times row 3 plus row 1 to row 1. And we're going to have row 2 is basically unchanged. And then -1, -5, 1, and 17. These are all unchanged. Row 1 is 2 times row 3. Okay, added to any row 1 elements. That's going to be 0. And this is going to be -5. And this is 5, actually. So it seems that we have some decent numbers, actually. I don't know. Hopefully we do have decent numbers. Okay, and then we have 2 times 17 plus -10, which is 34 minus 10, which is 24. As you can see, we actually do have some regular looking numbers. Okay, so now we decide what to do next. I'm thinking we create our own pivot. All right. So we can't really use this pivot anymore because we already have a pivot in row 3, so we can't do that. But we can use the -5s, subtract them, right? And hopefully get like 0, right? And then let's see what we're left with. So actually, let's change of plans. We can actually use the row 3 pivot here, but except we have to use the effect on row 3 directly. So let me explain it real quick. So since we already have a pivot in row 3, pivot for z, we can't have another pivot in row 3, otherwise it won't be cleared. So we're gonna have to use we're gonna have to keep the -2 and get rid of the -1. All right, so let's do that. And the operation will be -2 row 3 plus row 2 to row 3. All right, so let's do it. So 24, 0, -5, 5, -2, -2, 2, 2. And then finally we have -2 times row 3 is going to be 2 plus -2 is 0 here. And then we have 10 minus 2 is 8. And then we have what? Um, Let's just see, -2. Actually, so we went here and we got rid of this one. I don't know what I was doing just now. We could have just went on with the game plan and just completed that, but actually, yeah, we could have done that, but I don't know. Let's experiment because usually the ones that they give you on tests are like specially chosen out to have a good outcome, but for this one, I just put some random numbers in. So I don't know what is actually going to happen, but as long as we have a pivot, we should be fine. Um, negative -2 plus 2 here. There's a 0 again. I don't know what happened there. Uh, we just got rid of our own pivot. So I don't think that's the correct one, unfortunately. Let's try something else. And let's see here. So I could probably just do the same thing, but add this to this, right? And get rid of both things at once. Get rid of both things at once. Maybe that's possible. That would be nice, wouldn't it? Yeah, that could be possible, I think. So let me see. -2 row 3 plus row 2, except this time it's on row 2 directly. All right, so we're gonna have 2 plus -2 is 0 here. We're gonna have 8 here. And we're gonna have 0 here. Actually, we could have just switched rows. Okay, never mind that. This is quite uh, confusing. I don't know. So -34 plus 2 is just -32. Right, so we already have 1 here, and let's just get rid of that one. Let's just simplify this real quick. Just do 1/8 of row 2, and then we can see that y is actually -4 here. 0, -5, 5. So -4, as you can see, we created our own pivot here. So I'm thinking that since we already have let's use this pivot to get rid of the -5s. All right, and hopefully see what's over there. Okay, well, what we end up with, right? So let's just do that. We can do 2 operations at once, I'm pretty sure. So let's do 5 times row 2 plus row 1 to row 1. 5 times row 2 plus row 3 to row 3. And let's just see what we end up with, see if it's good or not. This is quite interesting. So it's with these matrices with Gaussian elimination, you always have to like experiment with it. That's why it's not that efficient. Because if you experiment with it and it doesn't go your way and you get really weird numbers, then you're just screwed. So today I'm actually going to teach you another way to solve systems using matrices, but without Gaussian elimination because it can be pretty annoying. So let's just check here. Anyways, 5 times row 2 plus row 1 is a 0, and then 5. Great. We got another singular one here. It's what 5 times -4 is plus 24 is just going to be 4, 20, 24 minus 20 is just 4. Here, as you can see, we got another variable. Okay, and then let's see. We have -1, 0, and then 1 here, right? So obviously we are going to let me see. This 5 times base 17 minus 20 is -3. Obviously, we're gonna keep this diagonal, right? And we're gonna have to get rid of this. So that is actually really easy. We're gonna have to use the 5 to get rid of the 1 because we want to keep the 5. Let's do that real quick. And the way we do it is it's actually I think -5 times row 3 plus row 1 to row 3. Okay, that's what we're gonna do. It's kind of disgusting, but whatever. So -5 times row 3 plus row 1 is just gonna be 5. 0, no change, and then we're gonna have a 0 here, and then -5 times row 3, which is 15. That's 19. This is super ugly. Finally, we get our answer. X is equal to 4/5. Y is equal to -4. Z is equal to 19. What? No, wrong. Z is equal to 4/5. X is going to be equal to 19/5. And I probably even made a mistake in there, somewhere in there too. So I don't know if this is actually the correct answer. Yeah, that's unfortunate. Actually, let's see. Uh, so we have 2x. Let's just check it with the first equation here. So we have 2 times x, which is already 38, over 5, minus 3z, which is 12 over 5. All right, and that's what is that? Minus 20, so that's obviously not correct. Yeah, I think we messed up somewhere in here with all the calculations. So it's very, very annoying to do this. But at least we kind of got an answer here, even though it's I don't think it's correct. But somewhere in there, these operations are correct. These operations are correct. You just need to check on all the calculations. I probably went wrong somewhere. And this next one is basically the same thing. So as you can see, Gaussian elimination, super annoying, right? But that doesn't mean that matrices are not efficient. For Gaussian elimination, I mean, it's good to do some other things, but it's not good to directly solve the system, right? It's going to be quite annoying, especially if you have like a fourth order system. You're probably not going to try to use Gauss-Jordan elimination to do that. It's going to be very annoying for you. You do not want to do that, okay? So now I'm going to introduce you to Cramer's rule, but first we need to learn about determinants, which are used in Cramer's rule. Determinants, every square matrix has a determinant, and the determinant is not a matrix, it is a number. So let's see what we have here. All square matrices have determinants. And that's denoted by by this, which looks kind of like an absolute value sign. It actually pretty much is an absolute value sign, but when we're talking about matrices, this means the determinant. of matrix A. Okay. If A is equal to a single order matrix, then the determinant of A is just equal to that element. But now this is the important part. This is the important part. If A is equal to a second order determinant, right? A second order determinant is important, so make sure you write this down. Then the determinant of A is just going to be as you can see, the determinant of A would be equal to A11 times A22 minus A21 times A12. So what did we do here? If you're observant, we can see that we cross-multiplied them and subtracted them. So we multiply the top left corner with the bottom right corner and then subtract it by the product of the top right corner and the bottom left corner. So that's how we do it. Make sure you take notes on this, all right? Before we go any further, just make sure that you know what you're doing. Okay? So here's some example problems. All right, I'm going to give you like 1 minute to do this. Make sure you find the determinant, all right? And this is how you find it, okay? So I'm going to give you a couple moments to do that, then I'll come back and check. Ah, yes. William, I think you caught my mistake, I think, just now. In the last problem, I think, right? Was that? Yeah, anyways, yeah. So last problem, I probably made some mistakes somewhere. Yeah, anyways, see how it's very inconvenient to use Gauss Jordan? There's so many numbers here, especially like some big numbers like 24, -32, and 17 here is it's quite difficult. That's why I'm going to introduce you to determinants. So let's just do this real quick. This is -6, right? And then that's minus -20. That's 14. And then we have 18 minus 32, and that's just going to be 18 minus that's -14. Yeah. Okay. So apparently they're both 14. I don't know what happened there. A lucky coincidence. That's nice. Okay. So now let's move on. We got to do this quick if I want to fit it in the time period. So anyways, element minors. So element minor, the minor of a of a determinant is basically the matrix obtained by deleting the row and column of the element. Right. So let's do this. Okay. The minor of, for example, A23 in the determinant of of something like this, right? Okay, so let's just say this example matrix here, and we want to find the minor of this specific element, A23 here. Okay, so in a third order determinant, it is a second order determinant that is obtained by deleting the row and column containing the element. So what does that mean? We're deleting the row and the column, meaning we're crossing out this and we're crossing out this. What is the determinant that we're ending up with? It's going to be equal to A11, A12, A31, and A32, right? Because we deleted everything else. We deleted everything else. So we're left with these, right? So this is going to be the minor. So A11, A32 minus A31, A12, right? Okay. So that's what we have here. And for example, if you wanted to do the minor of let's just practice a little bit more. The minor of A31, right? We're going to eliminate the row and the column of it, right? So all we're left with is A12, right? And then A13, A22, and A23, as you can see here. And then that's just going to be A12 times A23 minus A22 times A13. So as you can see, minor, not that hard. The minor is not that hard, which is basically this is for like third order determinants, but you can also do this for like any order. So if you have a fourth order determinant, you're still deleting the row and the column, right? And you're going to get the minor would be a third order determinant in a fourth order determinant, right? So, but we're gonna mostly work with third order determinants in this unit because usually when we learn, we use third order because they're complex enough to be more complex than second order determinants, which usually have some shortcuts, but they're also not too complicated, so we can work with them. All right. So now let's look at the cofactors, and this is closely associated with the minor of an element. So of row I and column, let's say column J, the cofactor of an element is what? It's going to be -1 to the I plus j power, right, times the minor of the element, aij. And sometimes there's actually a pattern that you can see here. So there's obviously a pattern, right? In a third order determinant, this is going to be positive, negative, positive, negative, positive, negative. There's positive, negative, positive. There's a pattern here. And by this, I mean like the -1. For example, -1 times to the power of 1 plus 1 obviously is a +1 here. So that's why this is positive, right? So you can find this pattern here. So now we want to find, and we want to multiply that times the minor of the of the element. So basically all we're doing here is just adding a sign to the minor. It's either going to be positive minor or it's going to be a negative minor, right? Okay. So if you have the same set here of, let's just say A11, A12, A13, A21, A22, A23, A31, A32, A33. Here, when we find the cofactor, first we need to find the minor, right? Cofactor is going to be equal to, let's just say cofactor of A22. Cofactor of A22, okay? So we're going to have, obviously we're going to eliminate this row and this column to get these four in our minor. That's going to be A11, A13, A31, and A33. Okay? And that's going to be multiplied by basically -1 times 2 plus 2. As you can see, A22 is the middle of this, and obviously it's going to be positive, right? So it's just positive. Just positive times this minor. It's just a positive minor, so you don't really need to do anything with the sign. If it was negative, put a negative sign. But this is just going to be equal to A11 times A33 minus A31 times A13. That's the cofactor. And now you can finally get on with basically finding the determinant. All right. The determinant that we need to find here. Basically, we're gonna have cofactors, right? So let's see here. Let me explain it this way. So let's use a matrix here. The same matrix. The determinant of this would be so how about let's just choose a row. Let's choose this row. Would be A11 times the cofactor of the element plus A21, the next one in this column, times the cofactor plus A31 times the cofactor. So essentially, when you're calculating a determinant, you must choose a row, any column, right? Or row or column that you want, right? And then you're gonna have to basically add all these terms together. So let me show you with an example. It'll be easier to explain with an example. Right, so let's just make a matrix here. Two, actually, yeah. 2, 1, -1, right? -2, -3, 0, -1, 2, and 1. That's our matrix. I'm gonna have to find the determinant. Right, so William, can you help me with this one?
Okay.
So which row or column do you want to choose to find our determinant?
Row 2. Oh wait, no, row 1. Row 1.
Why row 1?
Because it has a 1.
Well, we don't really care about pivots here. We care about zeros. Because you're going to have to multiply the element with its cofactor, right? So if the element is 0, there's no term. It's just a 0 term. So if you choose column 3, we're just going to have to add 2 terms, right? Rather than picking like row 1 and adding 3 terms. Because we're lazy and we don't want to do that. So we're gonna choose row 3, all right? So William, how would we do this? It's just going to be -1 times the cofactor. So what is the cofactor?
The cofactor is -1 to the power. So
Don't worry about the sign of the cofactor yet. What is the minor? Just tell me the minor.
the minor.
You have to eliminate the row, right? Eliminate the row and the column. So what is the minor?
Oh, so the minor is negative. I think it is -2 times 2.
Well,
Minus
yeah, let's just
-1
put it in a
times.
matrix form first, right? We'll deal with
Yeah.
that later. And by the way, now the sign of the cofactor is just positive, right?
Yeah.
Now let's do the next one. So 0 we can skip because we know that's going to be equal to 0. 0 times anything is 0. Now let's move on to 1. So 1 times the cofactor, what would that be? This element, get rid of the row and get rid of the column.
Oh. So that'll be a 2, 1, and -1, 2.
A -2 and -3, actually.
Oh yeah, -2, -3.
Right, and this is, guess what, also positive, so we don't need to do anything with that. This is -1 times -4 minus +4, actually. So actually, the determinant of this would
0.
uh yeah, hold up.
Wait. No, wait, it's -4 minus 4, right?
No, it's -4 minus Actually, no. What? I've been doing this wrong.
Wait,
What's
that's
wrong?
3.
Wait, it's 3. Yeah, it is 3. I don't know. Okay. I don't know what I was doing there. Okay, whatever. Next one is -6 minus -2. So this is what? -6
Um,
plus 2 is -4, right?
yeah.
So we're gonna have -7 times -1, which is 7 minus 4, which is equal to 3. And that's how we find the determinant of a third order matrix. And now let's go to Kramer's rule. All right, do we really want to do this? Yeah, let's do it. Okay, Kramer's rule. It's basically the same thing. You're doing the same thing with the determinants. You're basically yeah. Okay, so this is going to be quite complicated, but once you look at it a little bit, it shouldn't be too hard. Let's just say these are your coefficients, right? K1 is basically the constant. Right. So now this is K3. Okay. And Kramer's rule, right, has a couple of things here. So this is so D is going to be equal to the coefficient determinant, obviously. And that's just going to be a number, just a constant there, as you can see, which of course cannot be equal to 0. If D is not equal to 0, then we have X is equal to K1, K2, K3, A12, A22, A32, A 1, 3, A2, 3, A3, 3. As you can see, it's basically the coefficient matrix, but except the k's took the place of the x's, right? Y is going to be equal to what? A11, A21, A31, but instead of the y, it's going to be K1, K2, K3. And then A13, A23, A33, right? And that's over D, which is the coefficient determinant. And now, Z, of course, you can guess it, right? What is Z going to be equal to? Z is going to be equal to, let me see. Yeah. It's A11, A21, A31, A12, A22, A32, K1, K2, K3. As you can see, the K's took the place of the Z's over D. All right. Are there any problems? Any questions with this? All right. So this is, as soon as you find the determinants, you can solve any system very easily. And actually, if you have a graphing calculator or any higher advanced calculator, it can actually solve determinants. So you can figure out with your own graphing calculator or whatever calculator that you have, if it can solve determinants, it usually can. Any graphing calculator should be able to solve determinants, and then you can get this really easily. That's Kramer's rule. And we have a problem here. I don't know. I'm just gonna set it up, not actually solve it because we don't have enough time to solve it. So D is just gonna be equal to this. It's just 2, 5, 0, 1, 2, -1, and -3, -4, and 7. And hopefully that does not equal to 0. It probably will not be equal to 0, right? X is just going to be equal to 2, 1, -3. No, actually, no. The x's are replaced by 9, 3, 1, which are the k's. Then 5, 2, 4, everything else is the same. And that's just over D. Y is going to be equal to, the y column is just going to be substituted for the k's, 9, 3, 1. And then 0, -1, 7 over D. Z is going to be equal to 2, 1, -3, 5, 2, -4, but the z's are replaced by 9, 3, 1 over D. As you can see, the solution column, right? No, not this one. The solution column replaces whatever variable you're trying to find, as you can see, right? Are there any questions on this? Yes, William.
Well, how do you divide matrices again?
Oh, you're not dividing matrices. D is a number because the determinant is equal to a number, right?
Oh,
C. And also, this is also equal to a number. The determinant is going to be equal to a number like 2 or 3, and this is maybe like 4. Then you're going to have like 2 over 4, which is 1/2, right? Determinants,
okay.
again, are not matrices. They're numbers. Any other problems? If there are no problems, then that's all for today. And next class is the last lesson. So hopefully you understood this lecture quite well. Took a lot of notes, right? Notes is important. Otherwise, you will forget everything by tomorrow, probably. Okay. And I'll see you guys next time.